Hello everybody, this is video 5.2. We're going to be looking at decimal multiplication. Now, if we want to be really technical about it, everything we've been doing is decimal multiplication because it's all been base 10. But what the book is kind of getting at is we're looking at multiplication with numbers in the decimal places to the right of the decimal point. So it's exactly what you think it is, but if really want to be technical about it, it's all been decimal multiplication. So anyway, let's get started. So I just want to remind you to not start with the algorithm, and I'm sure that a lot of you already know the algorithm for multiplying numbers with decimal places. Um, so we're going to look at one problem kind of throughout these slides. So 2.3 times 1.8. So we're going to multiply these together. And so most of you already know we're just going to multiply this ignoring the decimal places. So 8 times 3 is 24. I carry the 2. 8 times 6, I'm sorry, 8 times 2 is 16. Add the 2 makes 18. Put in the 0 that we've already addressed. 1 times 23 is 23. So 4. And then this is 11. And this is 414. And then most of you already know we add up the number of place values to the right of the decimal point. There's 2 total places, so we're going to put the decimal point right there. So there's 2 places to the right. There's the algorithm. Now, for most of us, that's how we learned it. And for most of us, we have no clue why we did it that way. Why are we adding up these things and the same number there? We've already addressed this carrying, so I'm not going to harp on that too much more. So we've already talked about grouping and carrying and all that sort of stuff. But I want to really look at this part of the algorithm, why we add these things together and get this answer. So we don't want to start with the algorithm necessarily. I suppose you could start with the algorithm and then put the supports underneath and look at the modeling, but I'm a much bigger fan of sort of starting at the beginning and building into the algorithm, this sort of inductive approach where we start with the specific cases and then build to the generality. Um, so there's nothing to say that you can't do it the other way, that you can't do it the deductive way and start with the algorithm and then narrow down those cases and then understand it. But that's just sort of not my preferred approach, but there's nothing to say that you can't do it that way. So let's get started at looking at some models of why multiplying decimals works this way. So probably one of the most intuitive starting points for this would be to just look at this as fraction multiplication. I mean, it's what we just did. So it's a natural bridge to go from multiplying fractions to multiplying decimals as fractions, because really decimals are a specific case of fractions. All the denominators we know are going to be powers or exponents of 10. So if we look at our previous example that we just did, we had our 2.3 times 1.8. Well, we can convert these into fractions, and specifically into improper fractions. So 23 over 10 times 18 over 10. Now, if we wanted, we could also convert these into mixed numbers and make these 2 and 3/10 times 1 and 8/10, or we could even skip the improper fraction completely and go straight to the mixed number. And we've looked at models for doing this already. I mean, we've already kind of seen how we could set this up. We know this is our 2 and 3/10. This is our 1 and 8/10. So here's 2, here's 3/10, and I'm going to write this a slightly different way for reasons that'll be obvious. So this makes 3/10, this makes 16/10, and then this makes 24 100ths. So we got to call back to knowing why this is 100ths, why this denominator is a product. And so if you need to pull this out and look back at that sort of previous model where we broke this into tens, so we could break this into tens. All right, it's not the best drawing in the world. And so now we color this in. We want 3 of these. We want 8 of these. We want a whole lot of those going the other way. And so now we can look at sort of this intersection in here. So we can always call back to this model, and we know that this is 3 by 8 here, so there's 24. And then we know there's 100. This unit got broken into 100 pieces, so there's our 100. So there's our 3 times 8, and there's our 10 times 10. So I want you to think about almost like the genealogy of this model. We've got our multiplication model, which goes to our fraction multiplication model, which goes to our mixed number multiplication model, which is really just our binary, or I'm sorry, our binomial multiplication model, which is really just a distributive property, which now goes to our mixed number model, which goes to our decimal model. This is the reason why we build these models, is because they help create this cognitive structure for how we understand, how we explain, how students understand all these things. Algorithms by themselves, just sort of discretely, and that's discretely ETE, not EET, discretely. Um, it's hard for students to make them into structures. It's hard for students to make them into things. But these models, these pictures, in almost sort of a fractal way, build on each other, and we see these themes over and over and over again. So this is the reason why we want to teach mathematics this way, so students can see how all these pieces fit together. Anyway, so now we can add all this together. We can change now this into 160 over 100, this to 30 over 100. So we can do some equivalent fractions there and get this as an improper fraction. So this is 2, and this is 54, and then 160 makes 214 over 100. So that's 4, and 14 over 100, which is 4.14, which is what we got previously. So we can work through this way and get this answer this way. We could also take these improper fractions and build this model the same way, and it's not really any different than what we looked at previously in terms of multiplying improper fractions. And it's really not that different from what we're doing with the mixed number. We just have to sort of define our picture a little bit differently. So here's 1, here's 2. So here's 1, here's my 3/10, here's my 1, here's my 8/10. And so now we just have to remember that my unit is going to be this 1 block here. So this is 1, this is 1, this is 3/10, 8/10, 8/10, 24 hundredths. Why does that work? We can always come back to here and look at the same multiplication model to verify that. And most of you will notice that this is not really a whole lot different than what we have in the mixed number model. This is still, these 2 1s make this 2. These 2 8/10ths make this 16/10 or 160 over 10. This is still this. This is still this. So it's all the same thing. The real distinguishing factor is going to be whether or not you want to approach this as improper fractions or mixed numbers, or do both. It wouldn't be the worst thing in the world to do both. Some students are going to understand one model a little bit better than the other, and if you show both, then you have this great opportunity to show how they're really the same thing. And that's a key piece for students to understand, that it's not this or that, it's this and that. They are inherently the same idea. Anyway, so this reduces the same way we get down here. We got the 2, however we want to do this, 2 plus 3/10 plus 16/10 plus 24 hundredths. We're still going to get down to 2 and 214 tenths. Whichever way we get there, you might get, depending on how you do the simplification, you might get to some sort of intermediary step. But either way, we're going to get to this 4 and 14 tenths. And then we got to remember we started in decimals, so we need to end in decimals, and we get the 4.14. We can then look at how we've got one decimal place here, one decimal place here, and then after we do enough of these examples, again, we're going to start with this concrete piece, and we're going to abstract it out. And after we've done enough of these problems in this abstraction, we're going to start to notice that this decimal, or I'm sorry, this denominator and this denominator have a connection. And we know that if this is 10 to a power, and this is 10 to a power, that when I multiply those denominators together, exponent rules dictate that we take the sum of those exponents. So there's a little bit of a 10 to the a times 10 to the b equals 10 to the a plus b. And so that's where adding those decimal places comes in. That's why that multiplication becomes this addition, because of this exponent rule. And I'm going to guess that a lot of you have never seen this or had this explained to you, but this is why we add those decimal places together, not just because we were told to. There is an actual legitimate mathematical reason for it. Anyway, so this is sort of a big overview of this fraction multiplication model. And I know I'm tying a lot of things into this, but that's because a lot of things tie into this. I mean, there's a lot of pieces that go into making this model work. A much shorter method that we can look at for this is looking at sort of whole number multiplication with a dash of estimation. So if I'm looking at 2.3 and 1.8, and I want to figure out what this is, well, one method would be just to do 23 by 18 and just multiply this as whole numbers, like it says right here. And so when I multiply this together, I'm going to get 414. So now if I go back and look at my original problem, my 2.3 and my 1.8, I know my answer is going to use 414, but there's no way that a little more than 2 and a little less than 2 is going to make 414. So I can sort of estimate where this decimal place goes, and I got some options here. So I've got 414, which, okay, that's way too big. A little bit more than 2 and a little bit less than 2 is not going to make 414. 41.4, that still seems a little heavy. 4.14, that sounds about right. Now, some students are going to wonder, the more than 2, the less than 2, so that product is not going to make it more than 4 or less than 4. But we already know that this is about 2 and this is about 2, so my answer should be about 2 as well. These are little approximation tildes. They look terrible. So we know we should be in the neighborhood, not of 2, what am I doing? But of 4. Here we go. 2 times 2 is 4. So I should be in the neighborhood of 4, so this sort of makes sense. Whether it's a little bit more or a little bit less, you know, that we might not know. Certainly some students might argue, well, the 3 is greater than 2, more than this minus 2 is less than 2. So it makes sense that this would be a little bit more than 4. I mean, it's a conversation worth having for sure. If we go down, our next possible case would be 0.414. That's way too small. And by the time we get to this, I mean, it's just absolutely ridiculous. So we could use estimation to get an idea of where this decimal point goes. I'll tell you right now that estimation is one of the NCTM standards that doesn't get hit very often. And so if you can look for cases where you can talk about estimation, use estimation to get students thinking about using approximate answers to help in their problem solving process, all the better. I wouldn't start with this, and I certainly wouldn't use this as the only means of placing the decimal point, because students are going to work with numbers that are really, really big or really, really small, and doing this as a whole number multiplication just doesn't make an awful lot of sense to do it this way. Just the mechanics of it's just not going to work. It's not a very generalizable method. So for numbers like this, which have 1 or 2 decimal places, and then the whole number of values aren't that large. I mean, 23 by 18 isn't that big. It does give us a means, it does give us a window by which to see how to use estimation for this, but this is not really your end-all be-all method here. We could also use base 10 blocks with estimation. This isn't really a whole lot different than what we just did in the previous two cases. So again, my 2.3 and my 1.8. I'm going to do this as 23 by 18 and set this up with my base 10 blocks. And again, I'm not going to draw all the pieces just in the interest of time and your patience. So this would be my 1, this would be my 1, and this would be my 1, 2, 3. I'm going to make this look a little bit nicer than it does. Like that. So then this is my 1 here. And so then this is 1, 2. My goodness, what happened there? That's a little better. 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. All right. I wasn't sure if I was counting the rows or the lines. So we'll extend this down, this down, this down. There we go. So this is 1. This makes my 8/10. I said I wasn't going to draw all of them, and I drew all of them anyway. This is my 3/10. So once we have these blocks in place, it's a really important conversation to talk about what all these blocks sort of represent. And we can mark off this and this. So we know that these are going to be units because they're 1 by 1. So these represent units. And what's really interesting about this is if we were to sort of, you'll see these things sometimes where they have, let me draw this in a different color, where there's like a little T-bar that kind of goes like this. And you frame your product inside this T-bar. And so students can kind of set up, we use a sort of light blue here, they can set up on this side of the T-bar the linear measure of what these things are. So they can set up their 1 and then 8 unit blocks. And what's interesting when setting this problem up this way is that we have to understand that this long was a unit in the factor, but in the product, the flat becomes the unit. And so unlike when we were doing this with whole numbers, and these things sort of stayed the same to a certain extent, in decimal multiplication, these values are shifting. And so the value of each of the pieces shifts a little bit as well. In the same way, this individual block here was a 10th, but when we do this multiplication, now the long is a 10th. And the same thing is true here. This was a long times a unit. And so it becomes this long. This long here was a 1, but now this long is a 10th. And then these units, which were tenths as factors, now become 100ths. So these pieces are going to equate to different values, whether they're part of the factor or part of the product. It allows us to use this physical, concrete, tangible model that we've used before, so that's a pro. The fact that these place values sort of shift a little bit is maybe a little bit of a con for some students. I think it's understandable for most students, but it is an extra moving part that you may or may not want to deal with. So it's just an idea. It's an idea to look at, but whether or not you want to use it, I would say at your own discretion. So eventually we get to the algorithm. We've already looked at it. But we can also think about this algorithm, this 2.3 times 1.8. We can look at intermediate algorithms to this. So at the very beginning, I just did like the full-on algorithm. I can do this as an expanded form, 2.3 and then 1 plus 0.8. And now we can do this as sort of a distributive property type problem. So 2 times 1, and then 2 times 0.8, and then 0.3 times 1, and then 0.3 times 0.8. And now, really, this is the same as the 4 regions that we've already seen in our model. We should recognize this 2.1, or the 2 times 1 goes there. The 2 by 0.8 goes there, and so on, so on, so on. So it's not really anything different. It's a more abstracted form of it because we're doing it purely symbolically. This you can explain, this you can do, this you can do. We've already talked about how to do whole number versus decimal multiplications. This is the only kind of tricky part that you sort of have to explain because you're doing decimal multiplication to try to sort of explain what's going on, and so you have decimal multiplication in your decimal multiplication. So what this does allow you to do, though, is focus on just this smaller part of decimal multiplication and pull this piece out. And so it's the same little diagram that we looked at before, the 3 and the 8. So here's our 3/10, here's our 8/10. And so we can look at this sort of cross-hatched piece in here and talk about how to get this as not 2.4, which is what a lot of students are going to want to make that, but that it's 0.24, that it's 24 hundredths, not 24 tenths. The idea that this is a tenth and this is a tenth, and so the answer should be in tenths, or the fact that 3 times 8 is 24, this has 1 decimal place, this has 1 decimal place, which is the same idea because they're just talking about tenths, but in terms of decimal places. 2.4 is going to be the really common incorrect answer for this. So why is it 0.24 instead? I mean, that's going to require some explanation for some students. So just be prepared for that. And again, this model helps support that. We can see we've broken this unit into 100 pieces, so that's why we're in hundreds. Anyway, so here's your checkpoint problem. 4.03 times 0.15. Think about how you might model that. Again, this is going to be a little bit tricky to do because now we've got these 3 place values. So the base 10 blocks might be a little bit harder to manage. And so think about how you're going to be able to model this. You may have to start with an intermediate model, which is not necessarily the worst thing in the world. Think about how you would have started with tenths problems like we did and built that up. So you would have already gotten to a point of abstraction to where you can kind of start at an intermediate point with this problem. But I want you to think about how you would model and solve, not just solve. I'm not so worried about the answer. I'm more worried about how you would explain and present the answer. So as always, if you have any questions, by all means, please feel free to ask in class or in office hours. Thank you.